This is Family 5, stall turns. Stall turns, commonly referred to as hammerheads, are some of the most graceful figures in the Aresti catalog. Shown here in its most basic form, the aircraft departs horizontal flight with a partial loop and draws a vertical upline. As the aircraft stops climbing, it pivots around the CG and draws a vertical downline. At the bottom of that line, another partial loop returns the aircraft to horizontal flight. Other elements can be added to the interior lines, making Family 5 a rich source of figures for the aerobatic pilot. Let's examine Family 5. Here are some examples of two-line stall turns. Hammerheads can be flown either upright or inverted as shown in figures 1 and 2. Both of these figures might be referred to as turnaround figures since the aircraft exits in the opposite direction of entry. Figures 3 and 4 are also two-line hammerheads with the exit in the same direction as the entry. Note also that these figures exit in a different orientation than entry. All of the radii in these figures, marked by circles, are 1/4 partial loops. Wind correction is required except during the stall portion of the figure. Here are examples of two-line stall turns with similar three-line figures. Figure 1 becomes a three-line hammerhead by adding a 45-degree line. Figure 3 becomes a three-line hammerhead in the same manner. Note that the 45-degree line could be added on entry or exit. When 45-degree lines are added, 1/8 partial loops, shown with circles, are used. Finally, some examples of 4-line stall turns from similar two-line figures. Figures 2 and 3 transition into figures 6 and 8 by adding 45-degree lines on both entry and exit. As with the 3-line hammerheads, when the 45-degree lines are added, the radii become 1/8 partial loops. Note the 1/2 roll on the figure 8 entry line. Any of the interior lines in hammerheads can have rolling elements added for an additional challenge. Now let's look at the stall turn considering only the lines and radii. We'll discuss the pivot portion later. In Figure 21, there are two 1/8 partial loops and a single 1/4 partial loop. None of the radii need match. The partial loops do, however, have to be smooth and constant. All of the standard looping rules do apply. The lines, either 45 or 90 degrees, are judged for correct angle as compared to the true horizon and must be wind corrected. Downgrades of 1/2 point per 5 degrees are assessed for deviations. If there are rolling elements on any interior line, the element must be centered so the line segments before and after the element are equal. In Figure 21, there are full rolls on the 45-degree entry line and the vertical down line. They must be centered as indicated in Figure 21. Deductions for not centering range from 1 to 4 points using Figure 14 in Rule 7.1 to determine the downgrade. Any pendulum movements seen after the aircraft pivots is downgraded at 1/2 point per 5 degrees. For example, if the aircraft swings left and right of vertical by 5 degrees each, the resulting deduction would be 1 point. Let's turn our focus to the pivot portion of the stall turn. The first thing to consider is wind drift. Wind drift may occur while the aircraft is in a stalled or near stalled condition. Any drift at this time is not downgraded. It's likely, depending upon the wind speed and direction, that the downline will be displaced downwind from the upline. Once the pivot is complete, the new reference point for the vertical downline is established. Pilots may pivot in either direction at their option, resulting in a pivot of more or less than 180 degrees. Many times a pilot will choose to pivot into the wind but is not required to do so. There is no requirement for the aircraft to be vertical in the yaw axis before the pivot is executed. During the pivot, there can be no rotation or torquing of the aircraft. Rotation is deducted at 1/2 point per 5 degrees. 0 is scored if more than 90 degrees of rotation is seen. Let's consider wind correction in the pitch axis. From level flight, the aircraft establishes a wind-corrected upline. Note the angle of the nose into the wind. As the aircraft approaches the stall, the pilot must bring the aircraft perfectly vertical in pitch. During the pivot, only motion about the yaw axis should be seen. Displacement is likely due to the wind. As with a crosswind situation, there is no deduction for drift in a stalled or near-stalled condition. Once the pivot is complete, the reference point for the vertical downline is established. When flying speed on the downline is regained, the pilot re-establishes the necessary wind correction. At the bottom of the line, the aircraft returns to level flight. Note that the entry and exit radii can be different with no penalty. The ideal pivot point is the aircraft CG as shown here. There is no deduction, however, if the aircraft pivots within 1/2 wingspan of ideal. For pivots larger than the maximum offset, there is a deduction of 1 point per 1/2 wingspan. During the pivot, the aircraft remains in the vertical plane. Any torquing is penalized at 1/2 point per 5 degrees. Finally, we'll look at some deviations that cause a 0 to be scored. If the aircraft flops when it reaches the stall instead of pivoting, the pilot receives a 0. A 0 is also scored in the case of a flyover. A flyover is characterized by continued vertical movement along with a pivot larger than 4 wingspans, as indicated in Figure 23. Judges must be careful to recognize an apparent flyover that may be partially caused by wind drift, especially should the pilot opt to pivot with the wind. Lastly, a 0 is awarded if any visible backward motion of the aircraft is shown, as in a tailslide. This concludes Aresti Family 5, Stall Turns. For more information, log on to mini-iac.com or arestisystems.com.